All right, so what we're doing today is we're going to review Wednesday's lessons, little mini lessons we had. And I have one more little mini lesson for you. And then what we're going to do is on Monday, all day Monday, we just review what happened to Table 1, what happened to Table 2. Now, I would like for you to be successful in this lab test. But here's the way you're going to do it. That sheet that I gave you, what you're going to do is you're going to, this weekend, try to fill up as much as you can. There's some of it you won't know. You'll say, I don't remember it. And then that's what we'll do on Monday. On Monday, when I review it, you'll say, I already got that. I already had that written down. I already had the balanced equation written down. I know the balanced equation. That's what's on the lab test. One of them will say, write the balanced equation for this lab right there. Okay, so let's go ahead and let me get back on my camera thing here. And this class is not going to last very long, so I know you can pay attention for 20 minutes, 25 minutes. So here we go. All right, so here's this kind of a complicated graph, and we're going to try to make a complicated graph not complicated. So help me out. See if you can answer my questions, all right? On this graph here, the x-axis says reaction progress, meaning time. Is that correct? So where would I find the reactants and where would I find the products? What are these and what are these? If this is before the experiment happened, before the reaction took place, and this is when it's done, then these are what? Reactants. What are these? Products. And same thing here. What are these? And products. And even the one you did down here, reactants and products. And I got that down. Now, energy is, every chemical has energy in it, but some have less than others. Like dynamite has a lot of energy in it, and water does not. And that has to do with chemical bonds and stuff like that. So let's just say that the reactants had 50 units of energy. I just made that number up, didn't I? But when it got done, it only had 25. What does that tell you? Say it again. It gave off. And what do you call a reaction that gives off energy? Exothermic. There are lots of exothermic reactions. Every time you light fire in a fireplace, isn't it exothermic? Burn gasoline, exothermic. I haven't seen, there are some endothermic ones. Have you ever been in an athletic event and they didn't have any ice they didn't have a concession stand, and somebody sprained their ankle or something, turned their ankle? And what are you going to do for ice? Have you guys ever seen these little chemical packs? And you just kind of hit it, and one chemical breaks into another, and you start touching it. It's cold. And they didn't put it in a refrigerator. It's cold because the reaction was what? It didn't give off energy, what? Endothermic. It took in energy, right? And so there are a few of those endothermic reactions. Now, what I would like to show you, and we're going to relate it to some of our labs, all right? Table number 1, why did you have to put the copper into the flame? We wanted the copper to react with oxygen, didn't we? Is that what we wanted? Look at here. And you don't have this filled out. I'm going to fill this out for you on Monday, okay? But if you do this over the weekend, what did you want copper to react with on Table 1? The oxygen from where? The air. Excellent. And what did you want it to make? He said, well, God determined what was going to be made, but I looked it up. And what was the product over there? And which copper oxide? Because it's not always metal. Everybody look. Copper 2 oxide. Is that correct? Now, why didn't I just leave the copper on the table and say, go to it? React with the oxygen. What did I need? I could have used a catalyst. I like that. I like your thinking. In this case, I used what? Activation energy. Activation energy is how much energy you have to add, because right now the atoms of copper are just going like this. They're moving this fast, and when they bump into O2, nothing happens. Nothing happens. But what if you get the copper to move fast, 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 fast? And now they run into oxygen. Now what happens? Boom! Then they do form copper 2 oxide. Do you remember, not this table, but the next table? Didn't you have to heat those crystals? Why did you have to heat them? What's that called again? Activation energy. You know what I had to do? I had to do it. Now, Did I need activation energy over here when I put that nail? When I put that nail in a blue solution, did I have to heat it? No, room temperature was enough to let the reaction take place, wasn't it? How about that last table, or that next last table? How about when you pour those two things that look like water together and they made a precipitate? Did you have to heat that? No, room temperature was enough activation energy for it. What about this table here? You made this gas, this hydrogen gas, didn't you? And we wanted the hydrogen gas to react with oxygen. But what do we have to put in there? What do we put in that tube? Flame. So oxygen will react with hydrogen gas, but it needs some kind of a starter. See that? If I had a spark, I could use a spark, but I use a flame. Are you okay with activation energy? All right, now one more time. This is a separate deal. If you start with 50 units of energy and the products have 25, you must have lost 25 units of energy. That means you're exothermic. Now, some reactions take a lot of activation energy, like a Bunsen burner, right? Like a burner. And then here's one, I'm glad you mentioned that. At this table over here, I wanted this hydrogen peroxide to break down, to decompose. And I didn't put a flame on there, and room temperature wasn't enough to do it. So in this case, we use a thing, what is that called? A catalyst is a chemical that is not used up, but it causes the reaction to take place faster, right? And more likely to take place. And the catalyst there was that manganese dioxide stuff, wasn't it? And it's not a reactant, and it's not a product. That's why I put it on top of the arrow. See that? And so in this case, I can reduce. That's the question I always ask on the test. Catalysts work because they reduce the amount of what? Activation energy. That was this question here. A catalyst speeds up the rate of a chemical reaction by reducing the amount of activation energy. Is this all making sense now? And at the bottom here, what if you had to draw one that was endothermic? Well, I understand you put your products up here because they must have taken in energy. See that? If you went to school with $50 and came back with 80, what would your parents say now? They wouldn't say, where'd you lose $30? What would they say? Where'd you gain $30 from? And there are reactions like this, like photosynthesis. What does photosynthesis do? You take low energy carbon dioxide and water, and with sunlight, you trap that in chemical bonds, morons, and all of a sudden you got stuff called food. And it has lots of energy in it. That's very endothermic, isn't it? All right, you okay with this page? If you can answer all those questions, you're in good shape there. Now let's go to the next one. This chart here, I'm going to give you an example of one that might be on the test. Watch this here. What if I put this stuff and I reacted it with, okay, now, did everybody see that? Now, we did this last chapter. What kind of reaction do you think this might be? Say it again. Double replacement, right? Did everybody get that? We got AB plus CD. Okay. All right, Julia, help me out. Tell me one of the products. Remember, this guy here is a positive 1, right? And he's going to go kick out this other guy. It happens to be positive 1. Say it again. Silver?
Yeah, silver chloride.
Yes. Now, silver is +1, and chlorine's -1, so it's just a coincidence that's 1 and 1. Get that? What's the other one?
Sodium nitrate.
Not sodium. Oh, yeah. I'm sorry. Sodium what?
Nitrate.
Yes. Now, do you remember nitrate's -1? And what's sodium?
+1.
Okay. So it's just a coincidence that everything's 1 and 1, right? So it's matter it's already balanced, isn't it? Is the equation already balanced? Okay, got that. Now, I happen to know that when I make this, it looks like water. So it's clear. And this salt water looks clear also, doesn't it? Okay, now, I know when you mix these two, something's going to happen. So here's how you use this chart. This chart is only used for double replacement reactions. You can use it otherwise, but I use it mainly for double replacement reactions, and I don't look these up. I already know that these were aqueous, but I want to know about this. Okay, so everybody look those up. You have your chart with you? Or you can use this one. And the first part's positive, isn't it? And these are alphabetical. Silver, let's go down to silver. Silver and chloride. Chloride. Silver, It says S, and my symbols say S means you're going to be a solid. And what's another name for an insoluble product? What do you call an insoluble product? Starts with a P. A precipitate. Okay. Okay, so anyway, we have, it says here, so what should I write after AgCl? And will I see this? Will I see AgCl? Anybody know? It says it's going to be a solid. I had two things that look like water. I put them together, and I see something that looks like it's a solid. That's not like water. And let's look this guy up here, too. Sodium nitrate. Sodium, and these are alphabetical. Nitrate. What's it say for sodium nitrate? As a matter of fact, look at this right here. Sodium salts. These are all salts. Salts are ionic compounds, right? Every one of the sodium compounds, every one of them is aqueous. You'll never see it if you dissolve in water. You'll never see them. You'll never see sodium chloride in water. You'll never see sodium acetate in water because they're dissolved in water. So I'm going to put AQ after that one. All right. So this is called a double replacement reaction, but it also has another name. It's called a precipitation reaction because it has a precipitate. What's a precipitate? An insoluble product. Where do you find products? In a chemical reaction, where do you find products? Don't you have reactants over here, and what are these? Products. So I use this over here, don't I? And you know what? The one you did, do you remember the one you did? What's the one you did back there at that table? Let's take a look at it. Now this is actually a lab test question. It'll say, write out the balanced equation for the double replacement reaction, okay? Now, it's not till next Wednesday. You have plenty of time to study this, make flashcards, whatever you want to do. But one of them is called sodium carbonate aqueous. Now, carbonate's -2, sodium's +1. That's why it has to be Na2CO3. Does everybody get that? We had a whole chapter on that. Yes? Whoa. Sorry. All right, does everybody get that? So, sodium carbonate aqueous. What did it look like? You were there. It looked like water, didn't it? And then you mixed it with some calcium chloride. Calcium's +2, chlorine's -1. That's why you have to have 2. What did it look like? It looked like water. Now, without looking, can you tell me in your head what the two products are going to be? Just say the name of them. Don't tell me the formula. I'm going to call on, see, you weren't here. I don't know if that's fair, but Kyle, do you think you can do it? What are the names of the two products if it's double replacement? Can you switch these around? It won't be sodium carbonate, but it'll be sodium what? Yes, sodium chloride will be one of them. And what's the other compound? Say it. Calcium carbonate. Everybody got that? Now, how do you write those formulas? How do you write sodium chloride? You say, well, Na is +1. What's chlorine? -1. Hey, I got that done. And then what's the other one? Calcium carbonate. Calcium's +2. What's carbonate? -2. Yes? Say it again. Redox? Oh, I haven't even mentioned that to you guys. How do you know about redox? Oh, okay, don't worry about that yet. I haven't taught that yet. Okay, now, what I want to show you is, I have to balance this equation, don't I? What's the only thing I missed? What's missing here? If I had to balance this equation, what's the only thing I have to do? Everybody see that? Okay, now, what I want you to look at right here is the two products are sodium chloride and calcium carbonate. I want you to look them up. I'll give you this chart. You got that? I will give you this chart. So look up sodium chloride. He said, hey, wait a minute. I just looked that one up. What did you find out? It's aqueous. It dissolves in water, so I never get to see it. I won't ever see it because all the ions are all separated. It's dissolved in water. Can't see it. What's the other guy? Calcium carbonate. Look at that. What's that mean? No, not soluble. On this chart, S means what? It means a solid, right? S means it's a solid. So I had to put an S after this. Oops. Wait a minute. I had to put an S after this because what? What's that mean again? And what's the name of an insoluble product? What's another name for an insoluble product? Precipitate. Now, so anyway, this is called a precipitation reaction, also known as a double replacement reaction. Now, the question is, what did this look like? What does NaCl aqueous look like? It's clear, looks like water. And what did this look like? Very white, wasn't it? Matter of fact, another name for this is chalk. Calcium carbonate is chalk. Now, I know the chalk you probably had colors in it, didn't it? But you know what real pure chalk looks like? It's white. Chalk is white. Okay, what do you think? All right, now, I'm gonna hurry a little bit here. 1:15, okay, you can do it. I wanna show you another little mini lesson, okay? That's a little mini lesson, and I wanna show you how this works. Single replacement. Let's do double replacement. Double replacement, single replacement. What else you know? Synthesis and combustion and decomposition, right? That's what I taught you in another chapter, right? Now, I want to show you one other thing. One thing about chemistry, which was in that chapter I'll not teach you, is that you need something to kind of make the reaction take place. They call them driving forces. And the driving forces are the formation of water. Like if you didn't have water to begin with and you make water, the formation of a gas. You could have the formation of a solid. We just saw that. See that? We didn't have a solid. Formation of a solid, and that drives a reaction. And so if I'm going to show you this, 4 of the 5. This right here is the only one that's not, the driving force on double replacement is the formation of a solid. Now, what's that fancy name for the solid in a double replacement reaction? What do you call an insoluble product again? Precipitate. Okay, now, that right there, I'm going to draw a line here because that one, the reason that happened, do you know if both of these had been aqueous, nothing would have happened? There would have been no reaction, even though you wrote it down, even though you balanced it? If one of these had not been a solid, it wouldn't have happened. No reaction. Now, but I want to tell you about this one. The driving force for all four of these have the same reason why they occur. And what it means is that somebody's going to lose electrons. So somebody's going to lose electrons, and then somebody's going to gain electrons. Now, I'm not going to emphasize this on your lab test. Matter of fact, some of these are going to be bonus questions for you, okay? So this lesson here is going to help you get bonus points. Yes? Transfer of electrons? Yeah. Now, so I want to show you a little memory trick, okay? And I don't want to teach that whole chapter. I really don't. But when things lose electrons, we say that they were oxidized. Or you could say oxidation took place. And when you gain electrons, you say that things were reduced or the reduction took place. Now again, this is going to be for bonus points for you guys, okay? So I'm going to show you how this works. Every one of these has its own classification. Four of the five, the reason that they occur is that somebody gains electrons and somebody loses. Now scientists would call this reaction oxidation reduction reactions. Okay, now let's stop just for a minute here. Let's try it again, back up again. Of the five that you learned, one of them, nobody gains or loses electrons. The reason it works is because you formed a precipitate. As a matter of fact, this was +1, +1. Everybody keeps their charge the same and all that. All of these, somebody's going to change their charge by losing negative electrons, and somebody's going to change their charge by gaining electrons. You get that? Now, scientists call these four, besides the names you already knew, they call them oxidation reduction reactions. But because they're humans, how many times do you want to say that in a row? Oxidation reduction reaction. Oxidation, so say, who knows? They sat around one day, hey, can we say something shorter than that? And they came up with this word, redox. And I'm surprised you even knew that word. How'd you know redox? Okay, so what does redox stand for? Reduction, oxidation, you get it? Maybe they had oxy-re. I don't like that word. Redox. Nah, redox. I like that. And so a redox is a fast way of saying oxidation reduction. Now, what I'd like to do is I'll show you one of the reactions and what happened to it, okay? So let's take a look at this right here. And did you already have this written down? So this weekend, I'd like you to try to write down all the equations that you think you know, all right? For each of the reactions, say, I know what happened at that table. I was supposed to do research, and I look it up. I'm going to do that. Let's look at table number 1. Copper plus oxygen. Why did I say O2 here? Oxygen is a what? What's it called? Diatomic element, isn't it? Copper plus oxygen in the air with heat, activation energy, activation energy, yields, and which copper oxide? I'd look it up. I looked it up and I found out it was copper 2 oxide. Now, that is something you have to know. That's something that you should have known already, and you looked it up. Now, let me ask you this. How would you classify this? How would you classify that? Like last chapter. Synthesis. It is synthesis. But now you know that a synthesis reaction is also known as a what? Redox. So, what we're going to do is, here's a memory trick, okay? Leo the lion says, grr. Okay, now that's a memory trick, and what does it mean? What does Leo stand for? If you lose negative electrons, if you lose electrons, you become oxidized. If you gain electrons, you are reduced. You okay so far? Okay, now, who got Leo? And this is the hardest one, and I'm going to make these bonus points for you, okay? If you can understand this, I'll give you bonus points for these. If you lose negative electrons, don't you become more positive? So we got to find out who became more positive. So let me tell you the rules. There's a small set of rules. There's about 3 rules you need to know. Ready? We go back to the balanced equation, and we're going to sign these numbers. They're called oxidation states, and it's just a set of rules, okay? Rule number 1. If you are in an element not combined with any other element, you are assigned a number of 0. Is copper with anybody else? No, then you're 0. Oxygen, you with anybody else? No, you're 0. Now, if you're an ionic compound, like this guy, you get an oxidation state that's equal to your ion charge. What is the charge of copper in copper 2 oxide? +2. And what is the charge of oxygen in a compound? -2. That's always been the case, hasn't it? Now, here we go. This is the hard part for you. Don't look. Don't peek. Which element got LEO'd? Which element got oxidized? Which element lost negative electrons? And if you lose negative electrons, you become what? Who became more positive? Now, I'll show you a little trick. Another little trick, okay? You guys know number line, math class? Ready? -3, -2, -1, 0, 1, 2, 3. Which direction did you go to become more positive? To the right. So you're getting more positive, right? That's what I ask. Who lost negative electrons and became more positive? Look at the number line. I went from 0 to what? Woohoo! So who got oxidized? Copper. He went from what? 0 to +2. Yes. If you lose negative electrons, you become what? More positive. Who became more positive? On the number line. I did. So put a little copper here and put a 0 here. Now, look at this right here. Don't worry about the coefficient. Don't worry about those. Is it true that copper 0, that's copper metal, that's metal. Copper 0 turned into copper ions. Isn't that right? Isn't that an ion? How do you do that? How do you go from 0 and jump all the way up to +2? What'd you do? Did you gain negative electrons or lose them? I lost them. So he actually lost 2 electrons. Okay, so each copper lost 2 electrons to jump from 0 up to +2. Now, the only reason I have 4 here is because I had to look at the balance equation. Did you only start with 1 copper? And no, the balance equation said I started with 2, didn't I? And did you only end up with 1 copper ion? No, I ended up with 2. Well, then I had to change it to a 4. Get that? Okay, yes.
Why does copper start at 0?
Why does it do what?
Why does it start at 0?
Okay. Even though humans made up these rules tell you what's going on. I have a piece of copper right here. Everybody see that? Now, what's the charge on that copper? And I know what you're thinking. But one chapter we said copper in a compound can be either +1 or +2. Is this in a compound? What is any element when he's not in a compound? Is he an ion? No. So what is he? 0. So that's a great question you had. Any element not combined with another element is 0. It's not an ion. Now what about this copper oxide? Those are really ions, aren't they? Isn't that an ionic compound? Metal, non-metal, metal, non-metal. Remember that? We did that for a long time. So that's why you had to put 0 there, okay? Now, what about GUR? And I'm about ready to stop this lesson, but what about GUR? If you gain negative electrons, what happens to you? If you gain negative electrons, you become what? More negative. Now, look up here. Who became more negative? Who went this way on the number line? Oxygen? Okay, take a look. Oxygen went from 0 and dropped down to what? Oh, man. You went from 0 and dropped all the way down to -2. Now, how many electrons would that take? 0. Somebody must have thrown 2 electrons on you, right? And so I would have put a 2 here. And I would have if there'd only been 1 O. But how many O's are there? And since there were 2 oxygens, I have to have 4 electrons tossed onto me. And I end up with 2 oxygen -2s. Now, I didn't want to spend a whole lot of time on that. I did want to tell you this one more time. Of the 5 that you learned, only one of them does nobody change their charge. Nobody changed their charge in a double replacement reaction. You get that? But all of these, all the rest of these, they're redox. Somebody gains electrons, and somebody loses electrons. Okay. I'll tell you what. Let me see. We have about 1 minute. No, hold on. Here, I'll tell you what. Instead of me trying to teach another one, here's what I'd like you to do this weekend. I would like you to take this home and say, I wouldn't worry about the redox right now, okay? We can always do that again, but could you go home and at least try to fill in every bit of this that you know? If you said, I really do know it, I know the balanced equation for that table. I know that one. And if you don't, that's what we're gonna study on Monday, all day Monday. All I do is I go from table 1 to table 2 and I tell you what's going on. And that's what the lab test is about. And boy, I love, you guys are gonna get a good grade in your lab write-up, aren't you? Your lab write-up's gonna be done? Isn't your lab write-up gonna be done by Wednesday? There's something wrong if it's not done already, but it's to be done by Wednesday, right? And then you could get a good grade for the lab write-up and get a good grade on the lab test. That's great. And if we start something completely different, okay? All right, well, thank you very much.